Welcome to Zaption Tour 4.3, Patterns and Nonlinear Functions. This has 5 blocks in the lesson. So let's get going here. The concept here is we're going to be talking about the difference between linear functions and nonlinear functions, okay? A linear function is a function whose graph is non-vertical line or part of a non-vertical line. So whenever you see a graph that looks something like this right here, or something like this right here with dots, or even a line that is horizontal, then we know that we're going to be dealing with a linear function. The word linear, of course, just means line anyways, so it should make sense to us. Now, if we have a non-linear function, if we're dealing with a non-linear function, well, then the graph could look anything other than a line. So the definition for us as a nonlinear function is a function whose graph is not a line or part of a line. So it could look like a parabola, it could look like a cubic, or it could look like absolute value points. Anything that doesn't look like a line, we're going to call it a nonlinear function. That's the deal for box number 1. Box number 2 is an example talking about pizza. The area A in square inches of a pizza is a function of its radius in inches, and the cost, C in dollars, of the sauce for the pizza is a function of the weight, W in ounces. Graph these functions shown by the table below. Is each function linear or nonlinear? Okay, first thing I'm going to ask you to do is take a look at the pizza area table here that I've put a big red box around. Okay, we have radius and we have area. Those are our 2 variables that we're working with. I want you to decide which one is the independent and which one is the dependent. Hopefully you got that radius is our independent variable and area is our dependent variable. After all, the area depends on the radius, okay? Look at the sauce costs over here now in blue. We have 2 variables. The variables are weight and cost. So which variable is the independent and which one is the dependent? Okay, well, we know that the cost depends on the weight, so the cost is our dependent variable. The weight is our independent variable. Okay, now that we have figured that part out, I'm going to go ahead and make 2 graphs for you using the points that they have given us, okay? So the 2 graphs would look like this. The pizza area is a non-linear function, okay? Here's why. It gives us the points 0, 0. It gives us 2, 15. It gives us 4, 50, and so on and so forth all the way up and here. If we connect the lines here, you can see that I have this graph going up. This graph does not look like a line, therefore it is a non-linear function. The sauce cost, however, is a linear function because if I connect all the data points on the graph, I would get a nice smooth line. So sauce cost, this one would be linear and this one would be non-linear. Okay, box number 3 is a U-try, but I want to explain the U-try before I let you do it all by yourself. It says the number of cuts N and the fraction of the original area remaining A. So the points that they give us are A, or 1, 1/2, 2, 1/4, 3, 1/8, 4, and 1/16. So here's what they're doing. Let's say that this is a piece of paper. If I make 1 cut, then I only have 1/2 of the paper remaining. If I then make 2 cuts, I would only have 1/4 of the original paper remaining, and then so on and so forth. So that's where they're getting those numbers. Okay, go ahead and try it. Hopefully you figured out that this was a non-linear function. And if I graphed all my data points and I connected them all, I would get this kind of a curve. And if we have a curve, then we are dealing with a non-linear function. Box number 4 is an example. It says the table shows the total number of blocks in each figure below as a function of the number of blocks on one edge. So let me explain to you exactly what they're doing here. Let's take a look at this column. It says number of blocks on edge X. So I have 1 block on an edge, right? or one edge gives me one block, so therefore I have the pair 1, 1. If I have 2 blocks on an edge, then I have a grand total of 8 boxes, right? I have 1, 2, 3, 4, 5, 6, and then the other 2 in the back, all right? If I have 3 boxes on edge, then I have a grand total of 27 boxes, all right? So the question is, can you fill in these points right here and then in turn give me the ordered pair? So what do you think they are right now? Okay, hopefully you see that they are 4, 64. If I had 4 boxes on edge, I would have 64 total number of blocks. If I had 5 boxes on edge, then I would have 125 total boxes. Okay, so what I want to do is I want to graph the points that I have been given in the table and see whether or not this is a linear or a nonlinear function. Well, here is the graph of all the points that I've accumulated in my table. Well, from this picture, we can see that this is definitely a nonlinear function, and this is going up in some sort of a curve. So the next question then was, well, if this is going up as a curve, how could we represent this relation using an equation? So hopefully you see that there has to be a relationship between the inputs and the outputs, okay? If I put in a 1, I have to get out a 1. If I plug in a 2 to my function, I have to get out an 8. If I plug in a 3, I have to get out a 27. If I plug in a 4, I need to get out a 64. If I plug in a 5, I need to get out a 5. So what would I do if I plugged in a 6? Does anybody know? Well, I would have to take 6 and I would have to cube it, because that's what each of these numbers are, right? 125 is the same thing as 5 cubed. 64 is the same thing as 4 cubed. 27 is the same thing as 3 cubed, and so on. 8 is 2 cubed, and 1 is still 1 cubed. So therefore, we could represent this as y equals x cubed. That would be an equation that would represent this relation right here. Box number 5, I've got 2 examples here. I'm going to give you some ordered pairs. Ordered pairs are 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32. And we want to write the rule that represents this function. So here's what we need to do. We need to take all of the inputs, okay? 1 is going to get mapped to 2. That's what it says right there, okay? 2 is going to get mapped to 4. That's what it says right there. 3 gets mapped to 8. That's what that one tells me, and then so on and so forth. 4 gets mapped to 16, and then lastly 5 gets mapped to 32. So what we want to be able to do is come up with a relationship. So when we put in a 1, then out comes a 2. When we put in a 2, out comes a 4. When we put in a 3, out comes an 8, and so on and so forth. So we need to look for a relationship between the inputs and the outputs, all right? So I'm going to represent the number 2. This number 2 could be represented as the number 2 to the first power. This number 4 could be represented as the same thing as 2 to the second power. This number 8 is the same thing as 2 to the third power. The number 16 is the same thing as 2 to the fourth power. The number 32 is the same thing as 2 to the fifth power. Now I'm wondering if you're noticing that there is a connection between the exponent and the input, the exponent and the input, the exponent of 3 and the input of 3. So the exponent of 4 and the input of 4, the exponent of 5 and the input of 5. So if I kept going, if I gave you an x, what would x have to get mapped to? It would have to get mapped to 2 to whatever that power is. So the function rule that we would write would be y is just equal to 2 to the x power. Kind of an interesting one. Okay, let's take a look at this one. Okay, write the rule again. So again, what do I know? I know that 1 gets mapped to 1. I know that 2 gets mapped to 4. I know that 3 gets mapped to 9. I know that 4 gets mapped with 16. And I know that 5 gets mapped with 25. So can you come up with another way of relating the outputs? This is how I do it. I look at the outputs, okay? And I look for a relationship between the inputs and the outputs. Well, 1, 4, 9, 16, 25, those are all squares. So I could represent the number 1 as 1 squared. The number 2, or the number 4 is 2 squared. The number 9 is 3 squared. The number 4 is, or excuse me, the number 16 is 4 squared. The number 25 is 5 squared. So what's the relationship here? Well, I'm noticing that my base is the same thing as the input. My base is the same thing as the input. My base is the same thing as the input. 4 and a 4, 5 and a 5, right? So if I asked you, if I give you an x, what would you do to it? What would you map it to? Well, you would take the exponent, or excuse me, you would take the base, which in this case would be x, and you would raise it to the power of 2, right? So therefore, we could represent it as y is just equal to x squared, and that's how we get the answer.